So today we're trying to tackle the first problem on our fifth tutorial, differential equations. So yeah, let's just read what are they saying here. Consider an initial variable problem. That means they give us what is happening at time or whatever yes time not. Okay, this model may be used to describe a population dynamic of a fishery, and it is used in whatever the places that the equation for fish at harvesting time. Okay, this harvesting time, that's why it look like this, because your population linear model. So here they also included harvesting because they're taking something. They say solve for differential equation using separatable. Okay, let's see if we can do that. Let me try copying it first. Since we are trying to do separatable, so our main goal will be just separating every variable with p. So our variable here is going to be something is changing is p is depending on t. So these are variables. So anything that is not p or not t is considered a constant. So since we're trying to do separatable, so we were trying to take out a common factor here, p. Okay, that's good. And then if I take out p here, I'll be left with k 1 minus p close, and then here we also minus h. Okay, cool. What else? Okay, let me keep it there like that. Okay, dp dt is equal to like kp. Let me distribute that k inside. I'll have k minus kp minus h. So as I said, anything that doesn't have t or p is considered a constant. So this is a constant, this is a constant, right? So dp dt p k minus h is a constant, right? But we don't have p minus k p. So if this is a constant, let's call it some constant big R is equals to k minus h. So this thing really bring no value in terms of how we solve our problem, but what it just does, it's I don't know, it just make this thing easy on our eyes. Cool. So if that's the case, let me call this thing dp dt is equals to p open bracket r minus kp. Cool. So this is our new constant. This is another constant, but it's with t, so that term is p. That term is not really a constant. Okay, let's try to continue. So if it's separatable, anything with t, there's nothing with t, so t will be here alone. Anything with p will come this side, become dp, and then p r minus k p. All right, and then let's try to integrate both sides. All right, so if you integrate both sides here, this one is going to be easy. It's going to turn out to be some t plus some constant, but this is the elephant in the room. How are we going to integrate that? So the way to look, I think I should take advantage of partial fractions. A all over p plus b all over r minus kp, right? Saying this thing should equals to 1 all over p r minus kp, right? So we're going to take this term multiplied by throughout. So we multiply by the term throughout here. The p will cancel that p, will left with r minus kp plus this term will cancel that term, left with p here. P is equals to, then we'll have a 1 here. So the brackets here. Let me distribute AR minus AKP plus BP is equals to 1. Let me highlight everything that is not a constant. Remember, if you don't have P or T, you are a constant. This is a constant, this one has P, and P. This is the only one with a constant. And this side, this is a constant. So all the constants should equal to all the constants, if that makes sense. AR is equals to 1, then that thing will make my A to be equals to 1 over R. That's beautiful, right? So we can keep that one in a box. Okay, what is not a constant? Everything with P should equal to everything with P. So this guy has P, this guy has P, and this guy has P. Okay, you're wondering what that guy is plus 0 P. Alright, so I'm saying that the blue part, AKP plus BP is equal to some 0 P. No P's on the other side. Right, so P's are really not important. You can cancel them throughout. I'll have AK, I'm handwriting AK plus B should equals to nothing. Right, then I think there was a negative sign that I missed. This one, yes, I think here there's a negative sign. Then yeah, then we'll have already know what A is. A is 1 over R K plus, then let me put that B on the other side to become negative, and I'll lose that negative. I think I already say B is equals to K all over R. That's a beautiful one. Also goes inside the box. Thank you. So then if that's the case, remember for A we plug A, for B we plug B on that thing. Okay, then for A we're going to have 1 all over R P plus, for B we're going to have K all over R open brackets R minus KP close. Right, before I even try to integrate this, but I know that this thing will have some common factor, which is a constant R, and then I'll have 1 over P plus K all over R minus KP. That's a P. Cool. Then the goal is to integrate this, and I can still take the R outside. If I integrate that, I'll be left with ln P. And if I integrate that, I'll be left with K ln R minus KP all divided by negative K. Right, then I'll be left with R. Okay, this one will cancel that one, that will be minus. But now we can use logarithmic laws. Ln P, the positive part will be on top, this is the negative part, will be below. P all over R minus KP. Right, so this is our this side. And then remember, now we have 1 all over R open bracket ln P all over R minus KP. This thing is equals to, remember the T that we got, plus C. So we're literally continuing from this guy. So that is us continuing here. So what do we do now? We can multiply by R both sides, so we can have ln P all over R KP is equals to T R plus CR. So we can, Cristiano Ronaldo, we can just make him another constant. Let me call it C1. Right, then we can E everything, right? Base E everything. Right, this will cancel, then we'll have a P R minus KP, then this side will have E T R plus CR. Okay, let me just call it C1, we said. So because of less of exponent, we can just accept that this thing was like EC1. That's why if we add it become on top, but this thing is also a constant, become C2. So we can just cancel it out and write C2 here. We're trying to solve for P, right? Okay, then P will come here. Then see this thing beautifully as it is. Let me call it something phi. This beautiful thing this side. So I'll have phi r minus kp, right? And then p is going to equal to phi open r. Let me just disapprove that phi. Phi r minus phi kp. Then if that's the case, then this is our answer. No, not really. Take this one to the other p's. Then we'll have p minus phi is going to be plus this side kp is equals to phi r. Then we can factor out p. Will have 1 plus phi k is equals to phi r. Then now we're going to have p is equals to phi r all over 1 plus phi k. So we can bring back what phi was. Phi was that guy. So p is equals to c2 et. I think that's my etr. That is a big R multiplied by some r all over 1 plus c2 phi etr k. Some of the things here are already constant again. So this is going to be a solution. So if you bring back the question, they said solve for differential equation using separatable. So we've separated p, isolated and left it on the left, and everything that was none p was left on our right. So let's try to solve for second part of this problem. So the second part of the problem will be rewriting the DE as Bernoulli. Bernoullis look like linear. So Bernoulli is your y prime plus some p of x, and y is equals to some g of x and y n. So what Bernoulli does, take this thing and make it look so linear. Linear look like this: p x y is equals to some g of x. So without this part, this thing will look very linear. So if n is equals to 0, we make this thing 1 and this thing will be very separable. But if n is not, maybe it's 1, 2, whatever number is not equals to 0, this thing become if n is equal to 1, I forgot. Yes, if n is equal to non-zero, it's going to be your whatever Bernoulli that we're discussing, right? So if this thing was 0, this would have been 1, this thing would have been linear, right? It would have been, yes, it would have been linear, not separable but linear. The one that looked like it would have been like this, because this would have been 10 to 1. So that's all. So from the structure or the format of how Bernoulli equation should look, we'll try to write this thing as Bernoulli, if I should say. So I stole this part from the previous part that we've done before, because we've done and assigned this constant as k minus h big R. So let's try if we can make it look like Bernoulli. So Bernoulli is supposed to look like y prime plus some g of x, y is equal to some h of x and y n. So this we want it to look like that. And then we start with this dp dt, then I'll multiply, I'll have pr plus or minus kp p squared, then dp dt is going to equal to minus p r is equals to minus k p squared. So this look like Bernoulli. Yes, because this is my h function, this is my r is my g. Yes, look like 1, and n is equals to 2. Right, so Bernoulli does this thing of changing something that is Bernoulli to make it linear using a substitution. That's why in your book it's I think it's on chapter of 2.4.2.5 if I'm not mistaken, but under substitution. So solving differential equations by substitution. So we use this thing. So if this substitution u is equals to y minus 1p, but for our case I think it's easy to notice that our y is p, so p is our y, you see. So I think this will look better if I put p here. Then my n is 2, 1 minus 2, then I'll get negative 1. Negative 1 is same as that, which is same as p is equal to 1 over, let me write it like that. Then I can differentiate both sides. If I differentiate this one, I'll get dp dt, then become negative 1, u negative 2. I should have not written that negative 1, but 4, yes, then du dt. I get questions a lot how am I getting this? So this is literally chain rule if you think about it. Remember, if I can give you 2x squared and say differentiate this, you can differentiate the outside function, it's going to be 2x, and bring back the inside function unchanged, right? So this one will become 2 minus 1, giving you 1. Then you're going to differentiate what is inside. What is inside is what? You're going to say answer is 2x, but literally we're going to do dx of 2x. Then that look exactly as 2x and the 2 outside. So this is the same method that I'm doing here. I'm differentiating what is inside. So cool. So we know now what is this. We already said that is, so we can just plug it in. Negative u negative 2 du dt minus, we already defined p, this is p minus u is equal to minus k. We already defined p is going to be u negative 2. So when I'm here, I want to write it in a very linear form. I think I'll have du dt minus, there's an r here I think, and then I'll have, this will become positive because there's a negative, then this will become ur, then this will become positive because I'm developing k. Yes, so this is my new linear function. Then from here you can use your thing of we discuss e integral of p of x dx. Then you can use that to solve this linear function. So obviously you're going to take into account that I think in the beginning they gave us something they call first boundary condition. I think they have a good name that might call it boundary condition, or first, I think boundary condition. Yes, where they give us what is happening at time naught. So we're going to take advantage of that and solve for this linear equation. And then remember, after solving for this, you're going to get u in terms of t, and there will be blah 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 blah. But remember that we are trying to solve for p. You're going to use this translation to translate this function of u to bring it back in terms of p. So that's what in nutshell, that's what Bernoulli does. It take a function of y that is non-linear, make it a linear u function. Then after you got a linear u function, you solve a linear u function, then you're supposed to bring it back, translate it back into a p-world. Thank you.